So contagion is something that's really shaping all of our lives very much at the moment. And I want to talk about some of the processes and ideas that can shape our understanding of those different forms of contagion. So I'll talk about a number of different types of outbreaks and epidemics. But I want to start with a disease that's really had a huge impact on populations over time, and that is malaria. Malaria is an infection that's been with us as a species for a very long time indeed, but its name comes from medieval Italy. For a long time, people blamed these fevers on essentially bad smells in the air. And the name malaria comes from the Italian, malaria, bad air. And that was what people attributed it to. And you can see mentions of these kinds of fevers in a whole range of countries during this period. Actually, if you look at Shakespeare's plays, there's a lot of mentions of ague, which is the term at the time for these malarial fevers. And really from kind of Oslo to Ontario, you had these kinds of infections occurring. And people eventually traced the disease to this parasite, Plasmodium, that was making people ill. But the transmission process, the way in which these fevers moved through a population was still really kind of focused on bad air. But not all cultures had failed to see what was really going on. In the 1850s, for example, a British explorer called Richard Burton visited Somalia and noted that locally they had this perceived link between malarial fevers and mosquitoes. But Burton really dismissed it. He said that it was a superstition, that it was a coincidence, and that probably wasn't really the link that was driving the infection. And unfortunately, it would take many more decades for Western scientists really to get this idea and show that transmission was indeed via mosquitoes. And a lot of the progress came in the 1880s, 1890s, with a British medic called Ronald Ross, who was based out in India with the Indian Medical Service. And he'd become obviously very well acquainted with malaria as a disease. He was interested in mosquitoes as a potential route of transmission. But then there's that question of, well, how does it transmit from a human to a mosquito and back again? And Ross's initial idea was that it might happen via water somehow. He noticed that mosquitoes would often breed in water sources. So maybe it was the case that people were drinking water that somehow malaria-infected mosquitoes had been swimming in. And so what he did was he ran an experiment. He paid some volunteers and got water in which dead malarial mosquitoes had been in. He kind of fished the mosquitoes out, got these volunteers to drink the water. They didn't come down with malaria because, of course, that's not how malaria is transmitted. And gradually over time, Ross would refine his ideas and eventually, with some experiments on birds, showed that it was the bite of the mosquito. He could find the parasite in the saliva gland and could trace this route of transmission from an infected bird to the mosquito, really demonstrating this transmission cycle. He wrote to a collaborator afterwards, remarking that in retrospect, it's pretty obvious that humans don't go around drinking dead mosquitoes. But this link, this route of transmission that he had established was obviously crucially important for understanding the disease. But then there's the question of, well, what do we do with that knowledge? If mosquitoes spread malaria, can we control malaria by controlling mosquitoes? And at the time, there was a lot of opposition to these kind of suggestions, because the perceived wisdom was, well, if mosquitoes transmit malaria, then as long as there's mosquitoes, there's going to be malaria. You know, unless you can get rid of literally every last mosquito in an area or in a country, you're going to have some malaria transmitting. And Ross disagreed with this. And to show the logic of why that common perceived wisdom was flawed, he constructed a simple mathematical model of transmission. Essentially, his model was just laying out a hypothetical situation and working through the logic of what might happen. And he said, let's start with a situation where you have a village, there's 1,000 people, and one of them is infected with malaria. And in his hypothetical outbreak, he said, let's suppose that there's 48,000 mosquitoes in that village. And he said, well, not all of those mosquitoes will bite someone in a given period of time. Let's assume, say, a quarter of the mosquitoes end up biting someone. So 12,000 mosquitoes bite someone. But of course, in that village of 1,000 people, only one person's infected. So of those 12,000 mosquitoes, only 12 of them actually end up biting that infected person. But also, Ross noted that it takes some time for the parasite to develop in mosquito. It doesn't become infectious straight away. And that mosquitoes don't always have a very long lifespan. So probably, say, only a third of them would actually survive long enough to become infectious when they bit another person. So only 4 mosquitoes would survive long enough to be able to spread the parasites. And if you go back to that original assumption we had, well, only 1 in 4 mosquitoes end up biting someone. So only 1 infectious mosquito under this very simple model would end up biting another human. So although these are quite cartoonish assumptions, it shows that actually you can have a situation where you have 1 malaria case in a village of people, what seems like quite a large number of mosquitoes, but ultimately only end up with 1 additional infection as a result. And of course, if that initially infectious person were to recover over time, then you'd just have 1 infection and your outbreak wouldn't have grown. And then that opens the doors to really thinking about how control might work, because if you were to reduce the numbers of mosquitoes, you would reduce the proportions that are transmitting at each of these stages. So you wouldn't necessarily need to get rid of every mosquito. If you could reduce the numbers sufficiently so that over time, that number of infections wasn't growing, and that through those stages of transmission, the epidemic wasn't able to persist because the recoveries were occurring at a faster rate than the new infections, you'd see a decline. And this was his really crucial insight, that you didn't need to get rid of every single mosquito to control malaria. There's this threshold property. And once you got the outbreak below that threshold, you'd see a decline in transmission, even if you hadn't got rid of every last mosquito. And this way of thinking about diseases, of constructing these models, is obviously now something that's incredibly common. And we see a lot of modeling used in the study of infectious diseases. But I think it's always worth remembering that models aren't reality. They're really a simplified way of thinking about a problem. And often when I talk to people about models, I get one of 2 quite extreme reactions. I think sometimes you get people who are just very skeptical of them. They see them as these black boxes, these opaque, complex creatures that really can't be trusted. The other extreme, you get people who I think are sometimes slightly in awe of models. They think these are complex and clever, and they must be giving you the correct answer. And of course, neither of those 2 extremes is really the correct way forward. I think the best way of thinking of a model is a method for laying out the knowledge we have, the assumptions we can make from that knowledge, and the logical implications of those assumptions. So just like Ross did, where he said, if your idea is that you can't control malaria without getting every mosquito, let's lay out the assumptions, let's lay out those steps of transmission and see what the logic leads to. And really, I think anytime someone proposes an idea about how an epidemic works, every time they propose a control measure, they are implicitly using a conceptual model. Often they won't be laying out their assumptions clearly, but if someone says, I've got a great idea to control an epidemic, they are making a series of assumptions about how that epidemic works and what their control measure will be doing. I think often the value in a model is it just allows you to really make it clear what those steps are that are leading you to that conclusion. And as we've seen with Ross's model, you can sometimes get some surprises about where that ultimately ends up leading. What Ross did was really a shift in how people would think about epidemics. And later he'd build on that with a mathematician called Hilda Hudson and think about these processes of transmission. And an earlier way of thinking about outbreaks was really more of a descriptive one. So here, for example, we've got the swine flu pandemic in the UK. And of course, we could just describe the patterns as we see them in some form. So we could describe the peaks, the shapes of the curves. We could find some functions that maybe capture those shapes. But what's driving that pattern? What's the underlying features of transmission that are giving us this outbreak? And perhaps as you've already spotted looking at this, there's one very obvious thing that would explain, or perhaps obvious thing that explain why you might get a lull in the summer for flu pandemic. Swine flu was a pandemic where there was immunity in older groups, there was disproportionate susceptibility in younger individuals, and it meant that the school holiday coincided with this drop in transmission. And then later in the epidemic, you saw a small drop with half term, but probably also accumulation of immunity over that time period. And what a model makes it possible to do is, rather than this quite descriptive approach where we're just laying over different events, researchers could build a model putting in behavior of school kids, putting in the changes that happen over a summer holiday, and seeing if it could reproduce the epidemic. And it turns out that a model with data on social mixing in and out of term time does reproduce these kinds of patterns. But it also means you can ask what if questions. So the researchers who came up with this model also looked at what would happen if the school holiday hadn't been in place. And they found that actually the overall size of the epidemic probably would have been about 20% larger if these measures hadn't have existed. But we can also, by looking at the transmission process, start to quantify the extent of contagion that's going on. You see this very steep rise in the spring, it is in 2009 through to July, to that first peak. A key question for any outbreak is, how contagious is this new virus or this new event or whatever we're particularly interested in? And the number we use to measure that often in our field is one that's now very common, probably familiar to pretty much everyone, and that's the reproduction number. We define that as the average number of secondary infections generated by a typical case. So in other words, how many new infections are generated by one of the existing ones. And what the reproduction number does is it gives us a very natural division between two types of contagion. If the reproduction number is above 1, on average, each case generates more infection than there was before, and we see this growth over time. If the reproduction number is less than 1, then if you have a lot of infection at a particular point in time, then in the next point in time, you'd expect fewer than those infections and you'd see a decline. And if the reproduction number is equal to 1, then each infection on average generates the same amount as it was before, and you just get a flat epidemic. So you get these kind of 3 scenarios depending on whether it's above or below 1. And then obviously the further above 1 it is, the steeper the epidemic curve that you end up seeing. So how can we measure these kinds of values? Well, if you could just observe every single transmission event, you could just directly measure it. But of course, for biological contagion, that's very difficult to do because we don't observe every single exact transmission as it occurs. But there are outbreaks where we do have this information. One, for example, is online trends and online games. A few years ago, a prominent example was the Ice Bucket Challenge. And because these were public nominations, it was very clear who was doing them. Researchers could go back and trace these routes of transmission of who nominated whom to do the challenge. And this is a subset of people who did it. This is some celebrities. And you can see that most will nominate 1 or 2 other people. Some nominate 3, some won't nominate others. On average, the reproduction number is about 1.4 for this particular infection. And this doesn't perhaps seem that surprising, given that the reproduction number is actually hardwired into the game. For the Ice Bucket Challenge, people had to nominate 2 or 3 others. So you'd expect the reproduction number to be in that kind of range. It's slightly lower because probably not everyone ends up doing it. And there were other activities during this period as well. The Ice Bucket Challenge actually came slightly later from another game, which was in early 2014, which is neck nomination, where people had to down a drink, nominate other people to do it, and film it and put it online. It originated in Australia and then spread to a number of other countries. But both of these games had this property where the reproduction number was basically defined as part of the game. But it's not just the reproduction number we're interested in if we're looking at how an outbreak develops, because the reproduction number tells us at each step of infection how many new cases or how much growth in cases might we get. But of course, we also need to know the timescale. How long does that process take? And again, in both of these games, the timescale was inbuilt because people had 24 hours to do the challenge. And that means it's very straightforward to predict what that growth might look like over time. So if you have this delay in our field, we call it the serial interval. So it's delay from one individual showing symptoms to the person they infect showing symptoms. And then the amount of growth over that period is the reproduction number. So in something like an Ice Bucket Challenge, somebody does it, they nominate 2 other people, they say you have 24 hours to do it. So the serial interval is if everyone does it in 24 hours a day, that's the delay. And then over that time period, if 2 people do it, that gives you your reproduction number. So to walk through an example, say we have a serial interval of a day and a reproduction number of 2, as a lot of these games had. Then after a day, on average, you'd expect cases to double. And then after another day, you'd expect each of those cases to infect 2 more. And then after 3 days, on average, you'd expect 8 times more cases. And of course, eventually, within friendship groups, everyone will have done it. The activity would saturate, the level of susceptibility would decrease. But in the early stages, this gives you a pretty good approximation of how these outbreaks would grow. And certainly for all of these games, match very closely that initial growth that we saw. But this logic, this kind of simple laying out of these steps of transmission, also gives us a way to estimate reproduction numbers, because we're not always lucky enough that we have something like the Ice Bucket Challenge where the reproduction number and the serial interval are defined as part of the game. Often we don't know what the reproduction number is. We might be able to estimate what a serial interval is, but how do we get at this R value? Well, if we know how the epidemic is growing and we know something about the timescale, then we can try and work out what the R is by this kind of approach of looking at these steps of transmission. So if we have an epidemic curve, if we have a sense of when the outbreak started, if we have a sense of the timescale, so the serial interval, what's the step from one series of infections to the next, and we have an idea of how many cases there have been, then using that logic I showed on the previous slide, where we have this growth over time, we can use these pieces of information to work out what the reproduction number might be. It's what researchers did in the early stages of the coronavirus outbreak. But it turns out this part is surprisingly difficult. How many cases have there been over time? In the early stages of the coronavirus outbreak, there were about 40 cases that had been reported in Wuhan in China. But also by this point, 3 cases have been detected abroad. And so, of course, travel isn't that common, or certainly not common enough that of 40 cases, 3 would somehow be abroad. Some researchers at Imperial College constructed a model of transmission and how many cases might have been exported to other areas based on travel patterns. And they found that for 3 cases to have already made it into other countries, there were probably thousands of cases already in Wuhan that hadn't been detected by that point. And actually similar methods and similar insights provided early indications in other countries as well, actually, that transmission was far wider than the data were suggesting. We saw reports, for example, of export cases from Iran, from the US, from Britain, all of which indicated that there were probably more cases locally than the data at that point were suggesting. But going back to that early Wuhan outbreak, that if we took those estimates of the thousands of cases that were probably there based on what had been exported, if we took some early estimates of what the serial interval might be, in this case, researchers were using information from the SARS outbreak to get a rough idea, and of when it started, a number of groups estimated that the reproduction number was, in this case, perhaps around 2 or 3. As you can see, there's a lot of uncertainty in the confidence interval in these estimates. And that's reflected in this plot here, that, as you can see, there's uncertainty on the initial seed, so the initial size of the outbreak, uncertainty in the starting day, and uncertainty at where it ends up. So all of these are reflected in a lot of uncertainty around the reproduction number. But the key point isn't a specific number here. It's that you've got a number above 1. You're in exponential territory. It may be 2, it may be 3, it may be even slightly higher, which really emphasizes that this is something that's a threat that needs to be dealt with. So how does this compare with other forms of contagion? Researchers have used these kind of ideas for a whole range of different types of outbreaks and epidemics. And we can lay them out. We can take research that's been done and see how they compare. So here's a figure where I've put the reproduction number along the bottom, I've put the serial interval along the y-axis, and I'm just going to outline a few different forms of contagion that have been estimated in different studies. Just to give you a sense of how to interpret this figure, if something's in the bottom right-hand corner, it has a large reproduction number and a short serial interval, and that means that you're going to get a lot of new cases appearing over time because transmission's rapid and there's a really high magnitude to it. In the top left, events are much rarer because there's not much contagion at each step, and those steps are very far apart. So first of all, diseases. Well, To give three examples, so I mentioned the 2009 flu pandemic, COVID, and smallpox, which was eradicated in the 70s. If smallpox were to reappear in a susceptible population, I would have a higher reproduction number than the other two, but a slightly longer serial interval. We also have infections, though, that don't have this reproduction number above 1. So, for example, MERS and H5 bird flu have much lower reproduction numbers in humans. So they tend to kind of stutter in outbreaks. They don't take off exponentially. They just cause these small clusters before eventually fading out. But we can also overlay different types of contagion. As I mentioned, the ice bucket challenge comes in at about 1.5 in the reproduction number. The serial interval is actually slightly longer than a day. And that's probably because of the effort to do this, that people actually don't stick to the 24-hour time they're given. And generally it's about 48 hours take to do the challenge. And researchers have looked at a number of other forms of online contagion. For example, one group looked at email forwarding within a company. Obviously, very few company emails go exponential, but they often take a few hours for people to reply. Interestingly, Facebook researchers have looked at a number of different forms of really popular content on Facebook. Nomination-based content, so things like the Ice Bucket Challenge, typically have a longer serial interval and a reproduction number in that kind of 1 to 2 range. Pinned content, where you stick something on your profile or you pin it to the top, tends to spread quicker. And transient content, which is where people post and just hope that people will reshare it, spreads potentially very quickly indeed. But you'll notice that all of this popular content has a reproduction number in that range of around 2. So actually, it's very much the timescale that's driving things going viral, less than this kind of at the individual level having this really high amount of transmission. And actually, popular online content has a similar, certainly on Facebook, has a similar reproduction number to something like COVID overall. Studies have also looked at other forms of contagion. So, for example, a couple of studies have looked at violence, reproducing transmission chains of retaliatory gun violence in Chicago, or looking at copycat shootings in the US. And both of these, again, have a reproduction number less than 1. So if you have an event, on average, it will spark fewer than 1 additional events. And the lags are quite long. Gun violence seems to be of the order of months potentially, and then school shootings in the kind of week range based on these studies. And researchers have also looked at sort of innovations and ideas taking off, particularly scientific ideas, because if you can look at research papers, you can trace the citation network and you can look at how these ideas spread and take off. And some of these have had very high reproduction numbers. For example, concepts in physics, things like Feynman diagrams, quantum computing, have had high reproduction numbers, but longer serial intervals, because obviously the time scale on which scientific research happens and publishes is longer than you might see for biological contagion. But this all gives you a sense of the sort of a range of values we might see. Obviously, this is a small proportion of studies, and there's lots of other examples out there. But really, how we can differentiate between these different forms of contagion, the magnitude we see, the timescales that we see them occur on. But we're talking a lot about the reproduction number of infection. It's a reproduction number of 2. But what drives that value? Why does something have a reproduction number of a particular value? And we can understand that by breaking it down into the transmission process. So say, for example, someone's infectious. What dictates how many people they're going to spread it to? There's 4 components to the reproduction number. If you understand those 4 things, that really captures a lot of how contagion works. And so think about that person who's infectious. What's the first thing that really influences how much transmission happens? Well, that's the duration of infection. How long are they infectious with the virus for? It's not just the duration, it's what they do during that infectious period. So it's also the opportunities that are created for transmission while infectious. But it's not just the opportunities, it's the probability of transmission during that opportunity. People might meet each other, they might be wearing masks and PPE, they might not, and that will influence the transmission probability during that interaction. And then the final thing we need to consider is the susceptibility of the other person. You might have a conversation, the virus might get across, but if they're not susceptible, if they've been vaccinated, that transmission won't happen. So these 4 things are what I refer to as the dots. So duration, opportunities, transmission probability, and susceptibility. These are the 4 things that really influence the reproduction number. And there's this really nice property of them that if you multiply these four things together, you end up with the value of R. So you can see that if you change any of these four things, increase them or decrease them, then you change R proportionally as well. And that can give us clues about how we can control different sorts of infections, because we can target these different elements of the reproduction number. So for example, take something like HIV. HIV, we might try and reduce the duration of infection, because if people have treatment, then they're infectious for a shorter period of time. If people have fewer partners or change their sexual behavior, that might reduce the opportunities for transmission. If people practice safe sex, then those opportunities might still be there, but the transmission probability is much lower. And then in recent years, there's been much wider uptake of things like pre-exposure prophylaxis or PrEP, where people take treatment even though they're not infectious to reduce their susceptibility. And it isn't necessarily the case that one of these things will completely reduce the reproduction number below 1. But in combination within a population, each one of those can reduce R to some extent, and then the combined effect hopefully will be a controlled epidemic. So let's look at something like COVID. So similarly, COVID, you can think of targeting each of these different elements. So if someone is ill, we don't have a treatment that would reduce the duration of infectiousness early on at the moment. But if someone is isolated very quickly, then that has the effect of essentially reducing their duration of infectiousness. Social distancing reduces the opportunities for interaction. Things like masks, PPE reduce the transmission probability. And hopefully, in the next year or two, we'll have a vaccine which will reduce susceptibility and mean that we don't have to get this reduction from these first three elements of the dots. But again, it's not just infectious diseases. We could also think about online content and information. And again, different aspects of that will change how it transmits. So you might have, for example, the way in which something is posted. If it's pinned to someone's profile or not, that will change the visibility and the duration for which others could be exposed to it. The social links in a network, who your contacts are on Facebook or Twitter, will change the opportunities. The characteristics of a particular piece of content might change the transmission probability. You might have exactly the same set of friends, but one thing you share is far likelier to spread than another because of just the inherent characteristics of it. And then, of course, the final element is audience susceptibility. It might be that at a given point in time, people are just more susceptible to a particular message. I'm sure at the moment we're seeing a lot more content around infectious diseases that wouldn't have been nearly so contagious 6 months ago. But really understanding these different elements can not only just help us understand control, it can also, in some cases, help us evaluate a new threat. Back when Zika first emerged, there were these isolated reports of sexual transmission of Zika. And so people were saying, well, could this establish in a population? Could this become a new disease like HIV or gonorrhea or another STD? And one opinion piece in the New York Times asked, is this the millennials STD? And we did some work, and some other groups as well did, trying to answer this question. And we used this framework where we said, well, let's look at these different components of transmission. Let's look at the dots and see what we think they might be. Unfortunately, there's a lot we didn't know at the time, but based on evidence, the duration was probably quite short. It probably wasn't longer than about a month someone could be infectious, even if we were being pessimistic. From the opportunities, we could get data on partnerships, large-scale surveys of relationships and behavior. Susceptibility, we could assume, is probably quite near to 100% if we want a kind of conservative estimate. We didn't know what the transmission probability was, but we could look at other STDs. If you assume, for example, that Zika was even twice as transmissible as HIV at that particular point, then you wouldn't get a reproduction number overall that's above 1. And that's because the duration was relatively short compared to other STDs. So you might see a few transmission events, but it was unlikely to cause this major population epidemic. So our answer was, in this case, probably not something which is going to become the millennials STD, and others came to similar conclusions, and that's really been borne out over time. This is not a widespread disease in the absence of mosquitoes. But of course, to this point, I've been talking about reproduction numbers as this single number that we put on something early in an outbreak. But of course, reproduction numbers can change over time, as we've seen with infections like COVID and other diseases as control measures go in and out. We might see the value shift. So it might initially be an exponentially growing epidemic, but then control measures might go in and might reduce the reproduction number. And then over time, something might change. For example, control measures might be lifted and it might go back to something where we see a very fast growing epidemic, or we might see high risk activities, low risk activities, some balance of transmission leveling off and sort of changing how that affects things going forward. But we can use exactly the same methods I've described. If we're looking at how much transmission changes over a given period of time, we can use information on the serial interval to estimate what the reproduction number is and how that's changing over a period of weeks or months. And that's work that some of my colleagues have been doing for COVID. They've been taking data on reported cases and converting that into an estimate of the reproduction number. But there's a crucial intermediate step here that they have to do, because of course cases don't reflect when transmission is happening, because infections will have occurred and then there would have been a delay before people show symptoms and a delay before they get tested and they show up in the data. So the first thing we need to do is take the reported cases, that are the grey bars here, and then work out when these infections likely occurred. So it's probably a week or two earlier, and then use that blue infection curve here on the top plot to then estimate, based on this timescale that we know from the serial interval, what the reproduction number is over time. So I've used Singapore and Iran here as two examples where transmission has fluctuated over time. But of course, one of the things that's been quite a big challenge now is testing is changing. The amount of cases being detected are changing as well. And so getting this balance of understanding transmission patterns, but also getting a reliable indicator of what the actual underlying epidemic is looking like, is becoming harder. In particular, we could use data, for example, on hospitalizations or deaths, which perhaps reflect the underlying threat more clearly, but those data take longer to appear. And so we've already got a problem where the case data reflects transmission that was happening a while ago. So if we use other data sets, that lag gets even worse. So really, this is a key challenge in real time to try and estimate R very quickly, while also just being aware of some of the caveats. As I showed early on, case data is often a very hard thing to actually get a reliable indicator on. But it's not just changes that happen with things like control measures or changes in behavior. We can also see changes as viruses spread to new hosts and to new populations. For example, one study estimated that in late 2002, the reproduction number of SARS, based on some early cluster data in China, was around 0.8. By spring that year, the reproduction was much higher, almost 3. So it may have been that in that period, the virus adapted in some way that enabled it to spread more efficiently. It may have been that it was just in different populations and that helped it spread more widely. But we do see these changes. And bird flu, these infections that have an R below 1 currently, the concern is they may adapt to spread more efficiently. And this isn't just something we see with biological contagion. For example, a few years ago, this message spread widely on social media. And researchers who pieced together these chains of transmission, this is a message that was shared hundreds of thousands of times, noticed that there was quite high mutation rates. Actually, about 1 in every 10 posts would introduce a mutation into this message. So some posts, for example, added a personal element to the message. Some added a bit more detail for emphasis. Some added a bit more specifics about the timescale involved. And a lot of these changes increase the transmissibility of the message. So something that was initially spreading reasonably quickly would pick up these mutations and would adapt and spread further and faster. And we see this often with contagion online. But of course, to get something to deliberately evolve and take off is really hard, because obviously biological viruses have thousands of years of evolution behind them. They have often millions of opportunities for transmission and a potential to spill over into human populations and pick up these changes. To try and deliberately get something to take offline is clearly going to be much harder, because you don't have that mixing pot of evolution potentially generating things that are more transmissible. But there are examples of ways in which content can change online to become more transmissible and reach wider audiences. One example comes from a couple of years ago. This was a slogan that was adopted by the Republican Party. The slogan was "Jobs, not mobs." It was one which they were trying to imply that economics was being favored over immigration in their policy. The New York Times did this investigation and tried to trace where this meme had come from. They found that initially there were a handful of Twitter posts that weren't that widely shared with some of these words and some of these ideas floating around. And then a screenshot made its way onto Reddit. And then this in turn created follow-up memes, and people played around with the wording, played around with the imagery. And then one of these adapted memes eventually made its way back onto Facebook to some popular groups and started to spread there, and then got picked up on Twitter and started to spread, and eventually made its way onto Donald Trump's feed. And he ended up tweeting this element of the slogan, and then eventually it made its way more prominently into a lot of those political circles, and in turn spread widely on Twitter and Facebook. And we've seen this for a few different forms of online contagion, that in essence, some of these forums and platforms act like incubators, that you get a lot of variants of a meme generated, and then the most contagious ones and most contagious slogans will filter up and spread more widely. So it's almost analogous to what we see with this kind of natural selection process that can happen with biological viruses. But another key feature, though, is that process of amplification, that something comes from perhaps the fringes of the internet to prominence, often because one individual or particular outlet would have amplified it. So, for example, back in 2012, in July, rumors started spreading that the Higgs boson had been discovered. And each dot here shows a post during that early period of the rumors spreading, and the lines between them shows that someone has retweeted that post. So if you have two dots connected by a line, someone's tweeted, one person's retweeted it, and it just hasn't gone any further. And you can see here that these two almost super spreading events at the center of that early sharing, that most of the sharing doesn't go very far, but they're these two individuals who really spark and amplify the message, and then that goes much further and grows through the network. This is really common in Twitter outbreaks. Actually, most people and most tweets don't go anywhere. Most tweets that are put on Twitter just aren't shared by anyone. A lot are shared by maybe one or two people, not widely, and then this tiny fraction are shared really much, much further. And often when something goes viral, it doesn't go viral in the sense that something like the Ice Bucket Challenge does, where we have this sharing from 1 person to 2 to 4 to 8. Instead, there will be this super spreading event, this mass amplification event at the heart of it often. And there'll be one individual outlet that's really bringing this idea to a mass audience. And we see similar variation occurring for real diseases. If you look, for example, at COVID-19 transmission chains in Hong Kong, this is data from earlier this year, you can see, again, these dots are individuals, and the arrows are showing the routes of transmission. You have these 3 clusters on the left-hand side. You have a bar indicated by B, you have a wedding, and you have a temple. And the majority of transmission events in this diagram come from this handful of events. And we've done some work, and others as well, suggesting that 80% of transmission originates with about 10 to 20% of infections, often because of these events where there's a lot of transmission that can occur. And this creates this slight paradox, because most transmission, or most individuals, don't generate any transmission, both online and for a lot of infectious diseases. And that means that if you get, for example, a new case introduced to an area, generally it won't take off, because there's actually quite a low probability that it will generate secondary transmission, because most individuals don't infect anyone. But if it does spark a super spreading event, suddenly you've got a very big outbreak to deal with. And I think this is really an important central paradox to what we're seeing with a lot of COVID, that actually those initial sparks are less likely. So there could have been early on a lot of introductions potentially to places that didn't take off, and then one did, and then you saw very rapid growth. And I think this is going to be important for what happens next. As measures are lifted, I think some people have a perception that we're going to see this smooth growth and this smooth increase in transmission. We may well see that in some locations, but others, it may appear to be at a very low level. And then, as we saw recently in somewhere like Beijing, you get a flare up and then you get a number of cases appearing. So that dynamic makes it almost the potential for stuttering low level transmission and then very explosive growth, depending on whether or not these super spreading events can end up happening. But it can also shape how we view what causes them. Because, of course, if we go back to the dots, then variation in any one of these four things is going to drive variation in R. So as I've said, if a lot of transmission is coming from a handful of infections, that could be because of variation in the duration of infection, could be variation in opportunities, variation in susceptibility for transmission probability. And these are really important things to untangle. And historically, sometimes people have got it a bit wrong. For example, 30, 40 years ago, there were outbreaks of gonorrhea in Colorado Springs. And research had found that a fairly small number of people were linked to the majority of transmission. And some writers who noticed this and noticed these reports blamed it on the opportunities. They made the story that these individuals who were causing the majority of transmission must just have more partners than other people. They must just be more promiscuous, and that must be what's going on. And they made the story of it's other people to blame. They're not like us. They have too many partners, and that's the fault. That's what's causing this outbreak. But if you go back to the outbreak investigations, that's not really what seemed to be driving transmission. If you go back to those original outbreak investigations, the individuals who were seemingly causing this transmission, many of them were in fairly long-term relationships, and then within the town, people in wealthy areas who had a lot of partners weren't getting gonorrhea, and people who were in poor areas who had fewer partners were. And it turned out that one of the really important features was that a lot of the people involved in transmission weren't getting treated quickly enough. So in other words, the duration of infection was quite long. And so it wasn't so much the story that was being created about promiscuity. It was more that people didn't have access to the healthcare that they needed for one reason or another. And this was what was driving the reproduction number in those communities. And this idea of, I think, blame is a really important one, that when we see variation in transmission, it's very easy to focus on individuals. And sometimes that can be to the detriment of a public health response. Early on in the COVID outbreak, there was a lot of focus on China, a lot of really awful stigma directed towards Asian communities. And a lot of countries put in measures, focused very heavily on Asia as where the infections were coming from. And that may have distracted from really what was actually happening. If you look, for example, at genetic data on early outbreaks in the UK, here shows the estimated number of cases that were being imported over time into the UK. And these are importations that led to establishment of transmission. So there's well over 1,000 estimated importations during this period. But you can see that the ones coloured in purple from China are very, very small in number. And actually the vast majority in that early period were coming from Europe. And for context, Italy reported their first local transmission on the 21st of Feb, and then Spain was soon afterwards. So you can see that by the time that European countries had reported local transmission, you already had these importations occurring. So countries that were focusing on Asia perhaps weren't spending as much focus as they should have been on some of the other links within that network. I think really that's something that we can see. If you look at the flight network globally, there isn't just one route from one country to another. This is somewhere where you can have multiple routes between multiple countries. And this network structure is really important for how contagion might work, because if you have a network, for example, that's broken up, so on the right-hand side where these nodes, whether it's cities, whether it's individuals, aren't connected to anyone else, obviously contagion won't spread between them. But something like the flight network really links countries very closely together. But it's not just the links, it's also the existence of these loops. So, for example, it's not just the case that there's only one way to get from one country to another. You can actually go via other countries. So the existence of this loop means that even if you're focused on one of these links to another city, it may well be that the individuals could come via other routes as well. And this idea has been important in other forms of contagion as well. So back in 2008, I spent the summer interning at an investment bank, and that was the summer that the financial crisis really took off, and Lehman would end up Lehman Brothers going under at the end of that summer. And it was really an example of how these kind of network structures with these hidden links caused so many problems, because what happened during that period is there were a lot of exposures, either through loans between banks, or it was common investments in assets that led to problems with one bank percolating through the network and affecting others. But because it wasn't clear who owed what to whom and who was exposed to which bit of the outbreak, you had this complex network with these hidden links. It made the contagion much harder to understand, and it made really the network seize up because people couldn't piece together where these things were happening. But that wasn't the only feature of the financial networks during that period that was causing problems. A bit of research done in the 80s by researchers working on AIDS showed that network structure can be really important. This is work by Sunetra Gupta in the 80s, showing that if you have an associative network, so this is a network where essentially highly connected people are more likely to be connected to other highly connected people. Popular people hang out with popular people, essentially, in the network. In an associative network, the dynamics of an outbreak you'd often expect is one that would spread very quickly through these highly connected clusters, but wouldn't reach, or be less likely to reach, the wider network. In contrast, if you have a disassociative network, that's one where highly connected individuals are disproportionately connected to less connected people. And this outbreak spreads slower initially, but it eventually reaches a much wider part of the network because these hubs, these highly connected hubs, can keep it going and keep it really reaching far more widely. And this was the sort of structures we saw in financial networks at this point, that you had these massive banks who were connected to a huge number of other individuals. So when the crisis hit, it was something which could spread incredibly widely during that 2007-2008 period. And we've seen similar effects for things like malware online. If you think of a computer network, often it's structured in that disassociative way, that you have these hubs and these servers connected to many smaller machines. And that means that a lot of these viruses and worms can actually persist online for a surprisingly long period of time, even though they apparently aren't that infectious. And that's because the structure of the network really favors that kind of spread and enables these things to persist over time. So, of course, networks are really important to understand, and particularly for infectious diseases. We've done a lot of work, and colleagues are also during this period doing a lot of work trying to understand transmission. This is a study that we did originally a couple of years ago with the BBC to try and measure human social contact patterns in the UK. And subsequently, we've been applying it to aspects of COVID transmission, trying to understand how different contact tracing strategies might work, what level of effectiveness you might need, how these network structures might influence how many people need to be quarantined, what timescales you need to achieve that. And I think that's where these kind of values about transmission, these processes, really become crucial. And there's a paper published a few years ago, just to show you an illustration of this from it's back in 2004, but I think it's a really nice illustration of the challenge that's faced with contact tracing. So on the vertical here, you've got the reproduction number, so as I've talked about already. And along the bottom, it's the proportion of infections that happen either before people show symptoms or without symptoms. And essentially, as you move from the bottom left to the right, contact tracing becomes harder, because by the time a case appears with symptoms, transmission has probably already occurred. So on the left-hand side, you've got things like SARS and smallpox, where most people who are infectious have clear symptoms. So if you identify someone with symptoms, trace their contacts, quarantine them, there's a good chance you can contain the outbreak. Something like HIV would be much harder to use this approach, because by the time someone has clear symptoms, a lot of that transmission will have occurred over a period of time already. COVID and flu kind of sits somewhere in the middle. So flu, probably quite a high proportion of infections are prior to symptoms or without symptoms, which makes contact tracing very difficult. COVID sits towards the easier end of the scale, but not as easy as SARS. And that's what we've seen with really every country's experience with this, that contact tracing has worked to some extent, but often additional measures have been introduced alongside this. And the reason is that because you have this transmission before symptoms, by the time someone becomes ill, their contacts have already been infected. And so that means their contacts will potentially become infectious soon, and you're really racing against the clock to catch up with the outbreak at this point. And that's why a number of countries have started exploring additional measures and additional ways that they might be able to get ahead of transmission. And one thing that's been piloted in a number of countries, and it was proposed recently here, it may or may not go ahead. I'm sure there's lots of ideas that will be explored over the coming weeks and months. There's idea that if you could identify locations of transmission faster, then you might have another chance of getting ahead of the outbreak. So rather than just looking at cases that appear with symptoms and working out their individual contacts, can you actually work out places that people have been, which multiple individuals might have been exposed, as we saw with the flare-up in Korea recently with a nightclub, and a lot of people have been in that area were encouraged to get tested. And this idea of location being important is one that again can be traced back about 150 years, and traced back to, in this picture, by coincidence, this gentleman, John Snow. He was an epidemiologist who in the 1850s worked a lot on cholera. And the pub here is on Broad Street, now Broadwick Street in Soho. And in 1850s, there was this outbreak of cholera. And Snow tried to piece together what was going on. And to do that, he produced these maps of where the cases were happening. And this was his most famous map. Here you can see map of London. He's drawn these black bars to indicate in each house how many cholera cases there were. And the famous story goes that in his map, the cases cluster around this pump in the middle, and that was the evidence that demonstrated that the pump was responsible. But it wasn't quite that simple, because at the time, people blamed bad air for cholera. And so if you were going to draw a map of contagion spread by bad air in a given area, it would actually look potentially quite similar to this one. So Snow needed to do a little bit more detective work really to make the convincing case. So what he did was he said, well, it wouldn't just be in the area in the vicinity of a pump. It would depend on the nearest pump to people. So he worked out which would be the streets and the areas for which that Broad Street pump would be the nearest. And he drew what mathematicians call a Voronoi diagram, which essentially says the area within this boundary is for which the pump is likely to be the closest source of water. And this aligned very well with where the cases were seen. And he had additional bits of evidence too. So for example, you can see just to the right of the pump here, it's marked a brewery. And because they had their own source of water and no doubt drank the beer as well, they didn't have cases of cholera in the same way as the local area. And there was another crucial bit of evidence, which was a lady up in Hampstead who'd used to live in Soho. She liked the taste of the water from the Broad Street pump, so got it shipped up to her house in Hampstead, and she came down ill as well. And these clues that Snow pieced together were enough evidence for him to think that the pump was the cause. And he persuaded the local board of governors to remove the pump handle. And again, the story is that he removed the pump handle and the outbreak ended. But again, that's not quite the full story, because it turns out that when the pump handle was removed, the outbreak was already declining for one reason or another. Perhaps a number of people have been exposed, or perhaps some people had left the area, or a number of other reasons. And in my field, we often say to remove the pump handle as a synonym for introducing a control measure. But I think perhaps given this story, we should think of it as the right control measure, but one that's introduced too late. And even though Snow persuaded the local board of governors to remove the handle, when they later reviewed the evidence, they decided they weren't that convinced. And actually the handle was later replaced on the pump. And again, it would be decades before this link was really understood in terms of what was causing cholera. And John Snow wouldn't actually live to see his findings and his conclusions really accepted by the medical community. I think these stories I've told you about Contagion hopefully start to illustrate why we need to understand these processes, why looking at these locations and data in the way John Snow did was important, even though it would take time for this to be recognized, why being able to control mosquito populations gave insights into malaria, why elements of financial contagion were explained by network properties that STD researchers have been looking at in the 70s and 80s. Because ultimately, if we want to control an infection, we need to understand it. We need to understand how transmission works. We need to understand the features that are important. We need to understand those hidden links and those things that were driving past outbreaks. Because if we understand these things, then it gives us some chance of changing how these outbreaks happen in future. So, thank you.